All right. So here's some words that you've probably seen before, and let's try to set them up. Here's our idea. Let's say that we have a set, okay, and this set is well ordered, okay. Now imagine some kind of a subset. This is S naught, okay. And what I want is I'm going to pick an X here, and I'm going to say that this is an upper bound. And why is it an upper bound? The reason is that it's going to be bigger than every element of S naught. Okay. Now notice that it could be in S naught. It doesn't have to be in S naught, right? It just needs to be, quote, bigger than everything in S naught. And remember that the things are reflexive, so I really mean bigger or equal to. Okay. Now we can also have a lower bound right here. Okay, that is smaller than or equal to everything in the set S naught. Okay, I'm using a height here, right, to kind of give you an idea of less than or equal to, right? So this guy, elements up here are big, elements down here are small, right? That's just so that it's the picture makes sense. Okay, so I can find upper bounds, I can find lower bounds. Okay. And not always, right? Not all sets are bounded. For example, the set of all even integers is not bounded below, is not bounded above, right? But if that situation that we just drew there exists, then it is a bound, right? And here are some very simple examples. I have the set 4, 5, 6. I'm assuming just the simple less than or equal to ordering. And so 3 is less than or equal to all of these. All of those are less than or equal to 30, right? So we have an upper bound and we have a lower bound. Right, that's it. Right, there's nothing else to that. Okay, here's the set of even natural numbers, which of course has no upper bound, and we could also find things that have no lower bound. All right. Now what we're adding is the notion of least upper bound, okay, and greatest lower bound. So again, here's our set S naught, right? Here's our large set S. And we have here an upper bound. Okay, but what we want is somebody that's like right there. That might be the least upper bound. So to be a least upper bound, you need to have two properties. Number one, you need to be an upper bound. Okay, so you need to be above. It could even be inside the set, right? It just it just depends, right? Sometimes the set contains its upper bound, sometimes it doesn't. Okay. But you need to be able to be an upper bound. And by least, what we mean is that if you find some other lower bound, right, then this one is going to be greater than that one. Okay, so the least upper bound is always going to be less than or equal to any other upper bound. Okay, so those are our properties, right? That's what we mean by least upper bound. That's what we mean by greatest lower bound. Least upper bound, greatest lower bound. And let's take a look at some examples. Okay, so 4, 5, 6, I want a greatest lower bound, right? Here it is, right? This is actually an upper bound. I mean, sorry, a lower bound, right? Because 4 is less than or equal to 4, is less than or equal to 5, is less than or equal to 6, okay? And it is also a least or greatest lower bound, right? Because any lower bound has to be less than or equal to 4, right? Because 4 is in it, so we're done, right? Likewise, this here is going to be the least upper bound. Right? So suppose that I have an upper bound, 10, right? So 10 is an upper bound of this set, 4, 5, 6, right? And that's easy to see. I mean, it's bigger than all those elements. But not an upper bound, I should say a least upper bound, because 6 is an upper bound also, right? And 6 is less than 10, right? So that's what I mean by least upper bound. Okay, so those are words that we need to know what they mean. Okay, I do want to well, actually I should have shown you this example. This is a great example. because what we have is this is a greatest lower bound, okay, of the positive rationals. But notice that it actually doesn't belong to it, okay, and it's not the only such a set. Like for example, I think of all the x such that x belongs to Q, so it is a rational, right, and x is greater than the square root of 2. Right, let's say greater than or equal to, right? Well, if you look at that set, right, it's actually going to contain all sorts of numbers, right? But this will not contain the square root of 2, right? How come? Because the square root of 2 is not a rational number, right? So square root of 2 will be the greatest lower bound of this, right? Because all the elements in there are greater than or equal to it. And you can't, anything bigger than square root of 2 will actually not be a lower bound anymore. Anything smaller than it, right? Well, then square root of 2 is a lower bound, so by definition, anything smaller than it can't be a greatest lower bound. This is kind of the last word that we're going to define today. And what we're going to define is the word lattice, okay? And here's the picture that I always kind of think of when I think of a lattice, okay? Let's say that I have two elements, right? This is A and B, right? Then there's a way to get from A to B to something that's bigger, okay? So I'm going to call this A up arrow B, right? And this is bigger than both. And bigger according to our ordering, so that's actually equal. All right, from A and B, I can also go down and find something that I'm going to call a down arrow B, okay? And this is smaller than both. By the way, we call this a lattice because, of course, once you start having this, if there's any other point, then you can build the same thing, right? So this is C, A up arrow C, A down arrow C, and so on. And you see that it builds, you know, kind of diamond repeating patterns, right? Okay. Now, here's the canonical example of a lattice. Let's start with the set S. It actually doesn't matter what it is, right? And now consider the power set of that. Okay, so what's the power set? It's the set of subsets of S, right? And order it with subset, okay? And then if I take two A and B, right? So here I have that A and B belong to the power set of S. Alternatively, A is a subset of S, B is a subset of S, right? Then I can always find something that's, quote, larger than it by taking the union. Okay, so the union is bigger than both. And I can find something that's, quote, smaller than it by taking the intersection. Okay, so here we have a lattice. This is kind of the classic example of a lattice. There's others, okay? But the point is that lattices show up all over the place in computer science and mathematics. So this is a good place as any because we're right there at the definition to show you what they look like, okay? But we're not going to do much more than that, okay? I will ask you, go ahead and try to prove that this thing becomes a lattice. I already told you how to do it. You simply have to show that the union is bigger than either member, the intersection is smaller than both, and that should be quite straightforward.